Ladies and gentlemen, colleagues and students, welcome to the 2014 Shaw Prize Lecture in Astronomy at the Hong Kong University of Science and Technology. Professor Henry Tai, Director of the HKUST, Hong Kong Jockey Club Institute for Advanced Study, IAS, will represent the university to say a few words of welcome. Professor Tai, please.
I would like to welcome you to this Shaw Prize Lectures in Astronomy today, to be given by Professor Sean Koh of Professor of Physics, Institute for Computational Cosmology at Durham University, Professor Daniel Eisenstein, Professor of Astronomy at Harvard University, and Professor John Peacock, Professor of Cosmology at the Institute for Astronomy at the University of Edinburgh. These three distinguished scientists are the winner of the 2014 Shaw Prize in Astronomy. Established under the auspices of the late Sir Rowland Shaw, the Shaw Prize honors individuals, regardless of race, nationality, and religious belief, who have achieved significant breakthrough in academic and scientific research, and whose work has resulted in a positive and profound impact on mankind. It is one of the most prestigious prizes that can be bestowed on a researcher. Today's speakers and the laureates led the efforts in the Galaxy surveys. I think Professor Koh and Professor Peacock led the 2D field Galaxy Redshift Survey, and Professor Eisenstein led the Sloan Digital Sky Survey. These are two milestones in the progress of astronomy and cosmology. They won the prize for their contributions to the measurements of features in a large-scale structure in our universe, including baryon acoustic oscillation and redshift space distortion. To me, I consider the baryon acoustic oscillation to be one of the three pillars of modern observational cosmology. The other two are cosmic microwave background radiation and the accelerating universe, or sometimes we identify technically the type 1a supernova survey. In fact, the Shaw Prize was awarded to the team in type 1a supernova in 2006 and to the WMAP team on cosmic microwave background in 2010 already. And I'd like to point out that the team on the type 1a supernova who won the Shaw Prize in 2006 went on to win the Nobel Prize in 2011. Also, I would like to note that today's speakers, one, even though their research is on the same topic, one is a professor of astronomy, one is professor of cosmology, and one is professor of physics, telling you how the fields have merged and broadened the topic and compasses. The lecture they will give today is the topic called Cosmic Surveys and the Composition of the Universe. I will let them to explain why they won the Shaw Prize. Before I leave the floor to our distinguished speakers, I would like to thank the Shaw Prize for bringing the Shaw Prize laureates to our university every year. These lectures, after the Shaw Prize ceremony, provide a golden opportunity for our faculty and students to meet the great minds and be enlightened on the first hand. So we hope that this will help us to nurture students in the pursuit of knowledge and raise the community interest in the latest scientific discoveries. So I'm happy to some of your students and some of your faculty and to be interested in exploring, understanding these new, exciting discoveries, even though most of you are not in the field of astronomy or cosmology or physics. So, as a small token of appreciation, I would like to present a souvenir on behalf of the university to each of our speakers today. The souvenir is a miniature replica of the carved mural located at the sundial podium at the piazza. The mural depicts 29 ancient Chinese achievements in science and technology, one of which is the armillary sphere, an ancient Chinese instrument used to observe the sky. Actually, I was told that there's actually a replica on campus, which I think I know where it is. So HKUST has a splendid campus and a strong research culture, and we look forward to seeing the laureates to visit us again. So thank you. Yes. Okay, sure. So, cool. Okay, cool.
Thank you.
Yes. Okay, sorry. So, with the picture again, sorry. Okay. There we go. Okay. So, all three? Okay. It's up to you. So, okay. Thank you. Okay. I'm done.
So we'll begin the lecture right now. So can we invite the laureates to give the lecture?
Thank you, Henry Tai, for that very kind introduction for all of us. It's a real pleasure to be here, and thank you very much for coming to this lecture. Without more ado, let me explain that what motivates us as cosmologists is to answer big questions such as what is the composition of the universe, what is the dark matter and the dark energy that is in the universe, and how did structure form? An example of that structure, this is part of the 2DF survey, which I'll tell you a bit more about later, and it's quantitative study of the very large-scale distribution of galaxies that can help us answer these questions. So the Shaw Prize was given for our contributions to the measurement of features in large-scale structure, testing the cosmological model using baryonic acoustic oscillations and redshift space distortions. So part of our job today is explain all these things that are highlighted in color there. So we're doing a joint presentation, all three of us today, and it's a presentation by three people broken into two parts. So we're going to start with an introduction to cosmology and the large-scale structure. We'll present the observations from 2DF and Sloan, and then we'll move on to, after some questions, to testing the Big Bang in a quantitative way, introducing what we mean by baryonic acoustic oscillations, both in 2DF and Sloan, and ending with looking towards the future. So how that's split up between the three of us is as follows. So I'm starting on this part. Here we'll switch over to Daniel, and then in the second half we'll start with John Peacock, then myself again, then Daniel talking about Sloan, and John finishing up. So first, to orientate you a bit, to talk about what scales we're actually looking at in the universe. This here shows the Earth-Sun separation. We live in the outer part of the Milky Way galaxy. The scale between this picture and this one is more than a zoom of 6.4 billion. And the surveys we are going to show you are another 40,000 times larger than that. And if this works, got a brief... So this is a brief movie just orientating you, possibly. Yeah, there we go. So from the solar system, this is using real data, in fact. We'll take you on a journey from the solar system out through our galaxy and into the distribution of galaxies that was probed with the 2DF survey. I don't know if we can have the lights down a bit at the front. It will be better.
Lights down, please.
Yeah, that's better. So now we're zooming out of the plane of our galaxy. And this is, there are a billion stars in the Milky Way galaxy, but in the work we do, each galaxy is basically treated as a point that helps us trace the large-scale distribution. And here we're flying through the real 2DF Galaxy Redshift Survey, although the galaxy images you see are greatly exaggerated in size. When you're whizzing through like this, you don't see the structure in that much detail, but as we zoom out and pull back, you'll see the two regions that were surveyed in the 2DF survey, and the structure that those galaxies trace out is an intricate network of filaments and voids, which we will be talking about shortly. Okay, escape back out. Don't just hit PowerPoint. See, I don't normally use a Mac. This is Daniel's machine, but okay. So let's move on. So the first bit of physics that enables us to make these surveys is measuring the redshifts of galaxies. So a normal photon coming from a galaxy will be redshifted to a longer wavelength if that galaxy is receding away from us. So this is the Doppler shift, and defines the redshift is the fractional change in the wavelength. Observationally, how you do that is you get the spectrum of a galaxy, and if that galaxy is being redshifted because it's moving away from us, you'll see the spectral features, such as these calcium absorption lines, shifted to longer wavelengths. And so by identifying these features in the spectra and relating them to their rest frame wavelengths, you can determine the redshift and hence the recession velocity of each galaxy. So this is what Hubble used, so redshifts measured by Professor Slipher, enabled him to plot this famous diagram of distance to galaxies versus their recession velocity, and he found that this linear relation known as the Hubble law, that the velocity is proportional to distance. This is really what's telling us that the universe is expanding, all the galaxies are getting further apart with time. Just zooming into some more modern data, we see this linear relation holds out to very large distances. This is 500 megaparsecs, where a parsec is about 3 light years. So we're talking about 1 billion light years or so here. So this is what enables us to take surveys such as this of the distribution of galaxies on the sky and measure their distances by measuring their velocities and inferring their distances using Hubble's law, and turn that into a three-dimensional picture. And we'll be presenting some more details of that later, but the 2DF survey surveyed, so here we are in the Milky Way. We looked out in two directions, these two slices of the universe, and in those two slices, we were able to get the three-dimensional positions of the galaxies by measuring their redshifts. And you saw earlier, so this is the projection through the thin direction of this slice, but there's real three-dimensional information in that slice as well. And this is the movie you saw a little bit earlier. You see these voids and large superclusters in the overall distribution of galaxies. And this is intrinsically very beautiful when you see this structure, but we're today more interested in what things you can learn and measure by analyzing this structure. So the universe is expanding, galaxies are getting further apart from each other, but you can infer from that that in the past, the galaxies were closer together, the universe was smaller. And just like if you compress the air with a bicycle pump, it gets hotter due to the work you're doing, then this means that the universe, as you go back in time, was hotter, hence the Big Bang model. So the universe was very hot at early times and has expanded and cooled. And one prediction of that, as Professor Tai has explained, in fact, he's been a bit of a spoiler and told several things that I'm going to say, that the universe cools and eventually neutral atoms form, and at that point, the radiation travels unhindered to us across the universe because the plasma that you had at higher temperatures is now neutral and transparent to radiation. And this is the microwave background radiation that we observe. And it was measured in 2006 to be an extremely accurate blackbody spectrum showing its thermal nature. The error bars on this plot are very unlike the ones you do in undergraduate labs. They're actually 400 sigma error bars so that you can see them. It's a very accurate blackbody. So the one way to think about the expansion of the universe is in terms of this analogy, two-dimensional analogy of an expanding ball. Choose any point on that as where we are and rotate it round to the top. So if we're here, what we see is galaxies expanding away from us as the ball expands in this picture. And the further they are away from us, the faster they go. This is the nature of the Hubble law. The wavy line here is supposed to represent radiation from those galaxies being redshifted as the universe expands. So a galaxy that emits a photon at high redshift, by the time the universe is expanded, it's a longer wavelength photon by the time we observe it. So we use what are called co-moving coordinates to describe the positions of galaxies in the universe. So these are coordinates which expand with the expansion of the universe, rather like the purple lines painted on this ball. It's just a notional coordinate system. So in that system, galaxies that just move with that grid system stay at the same fixed co-moving coordinate. And all we have to take account of to work out their real physical positions is the expansion factor, which we define as A, which we can think of as being the typical distance between galaxies. So if galaxies the universe expands, so galaxies are twice as far apart, then A has doubled. And so we can relate the real coordinate system to the co-moving coordinate system X in this way. Simple differentiation then tells you that the velocity depends on A dot X for something just moving at fixed X. And so taking the ratio of these two equations, we see that we produce Hubble's law, where Hubble's parameter is actually just telling you about A dot, the time rate of change of the expansion factor. So this is going to be very important, working out how the Hubble parameter varies with time. So we used to think there were three possibilities for the universe. So the expansion of the universe is a balance between the initial impetus from the Big Bang that gives kinetic energy to all the material in the universe and the gravitational interaction of the material in the universe. So the more mass you have, the greater the attraction of that mass on it with every other particle in the universe. And if the density of the universe was high enough, we would expect the universe to expand, gravity would eventually win, and the universe would start to recollapse. But if the density is lower, then the universe would expand forever. And there's a critical density where it expands forever, but at a decreasing rate, which turns out to be about 5 hydrogen atoms per meter cubed. The mathematics of this is described, or the physics of this is described by Einstein's general relativity, from which you can derive the Friedmann equation, which relates how the Hubble parameter varies with time as the density changes and the expansion factor grows. The critical density is what you get if you solve this equation by setting k equal to 0, in which case the critical density is 3 times the Hubble parameter squared over 8 pi g. Which I say is roughly about 5 hydrogen atoms per meter cubed. And this is a very useful density scale for cosmologists to use, and so we often refer to the densities of matter and so on in terms of these omega parameters, which are just the densities in units of the critical density. So the evolution of the universe then depends on how that density evolves, which depends what the composition of the universe is. The mass in the universe decreases as the volume expands because mass is conserved. That means that as the volume goes up by a factor of a cubed, the density has to go down by a cubed. Radiation, on the other hand, goes down faster because the photon number density gets diluted in the same way, giving you a 1 over a cubed dependence. But each photon also loses energy because of the redshifting, giving you another factor of a. So although today radiation density is small in terms of its energy contribution to the energy density compared to mass, if we go back to earlier times when A was smaller, you eventually get to the point where the universe was radiation dominated, and the energy density in radiation was much greater than that in matter. So if we can measure how the Hubble constant evolves, Hubble parameter evolves over time, we can get constraints on the different contributions to the energy density in the universe. And one of the ways that this was done was the type 1a supernovae that were already mentioned. You treat those as a standard candle, and so if you know how bright they are intrinsically, and you can measure their fluxes at different redshifts, you can therefore work out the distance to those different redshifts, and that can give you a constraint on the evolution of the Hubble parameter. And as was already been said, former Shaw and Nobel Prize winners, looking very happy here, got the prize for doing this. So they measured this, basically the constraints on the expansion factor as a function of time by measuring the magnitudes of supernovae as a function of redshift, back to really quite high redshift. So you're seeing galaxies that are so far away that light has taken a significant fraction of the age of the universe to get to us, and so you're measuring the Hubble parameter as a function of time. And what I showed you in the previous equation suggests that the Hubble parameter should be decreasing with time, that the expansion rate should be decreasing with time. But what they found was we didn't live in any of those 3 models. We live in one in which the expansion rate is accelerating. And that requires an extra term in the Friedmann equation, a term that can here added on as Einstein's cosmological constant, which can be thought as the vacuum energy density contribution to the energy density in the universe. And if it really is vacuum energy density, then it's constant. The universe expands, you just have more vacuum. It hasn't changed the nature of that vacuum, and so its energy density is the same. But it could be something more complicated. It could be something that evolves with time, in which case we more generally refer that to as dark energy, with the cosmological constant, the constant value, being the simplest case. And so by measuring this expansion history more accurately, we can tell something about how dark energy evolves. So adding the dark energy. We don't know much about it, exactly how it evolved, so I've put on a few lines, but it's becoming to dominate recently in the universe. It's a function of expansion factor. It was totally negligible in the early universe. So the other topic that we want to explore and put into this model is how does the structure, everything from the desk in this lab to the moon and the sun, to the stars in our galaxy and the very large-scale structure that we trace out, how does that fit into this model, and how can we use it to constrain the composition of the universe? So the standard model for this is that these density fluctuations are generated by quantum fluctuations in the early universe, governed by Schrödinger's, Heisenberg's uncertainty principle. You have fluctuations in the energy density at any given point. And then there's this epoch of inflation that recently won the Kavli Prize, which stretches these microscopic fluctuations to macroscopic scales. In fact, to scales larger than the whole of the observable universe today. So this is the theory. It predicts Gaussian fluctuations, and these are what are observed in the microwave background. This is a picture from the WMAP satellite of the temperature fluctuations across the sky. And at that time, they're of order 10 to the minus 5, 1 part in 100,000. These then grow under gravity. So in this picture, we're looking at a co-moving volume in the universe, so the expansion has been factored out, time's clicking by, and those ever so small fluctuations you see at the start begin to grow under the action of gravity, clustering together, and then we put on some artificial rotation, you can see, producing filaments and voids and clusters. And we can evolve this system using supercomputer simulations representing the mass distribution and its fluctuations by a set of particles. We now can routinely run simulations with 100 billion particles and simulate with reasonable resolution volumes representative of the universe. So to finish the first part, the summary is we're working in this model that starts off with quantum fluctuations which are stretched to macroscopic scales by inflation. They grow under the influence of gravity and pressure, as we'll be talking about later, for the first 380 to 400,000 years. That's the epoch at which the universe recombines, the plasma you have early on becomes neutral atoms, and that radiation then propagates from the microwave background to us. After that, these fluctuations are amplified by gravity, forming the cosmic web of filaments and voids. It's this model that we want to test by mapping and quantifying large-scale structure in the galaxy distribution. So a little bit about the history of redshift measurements and redshift surveys. The early redshifts gathered by Slipher that Hubble used to detect the linear expansion law were only about 50 or so redshifts. This is because to get a redshift, you need to measure the spectrum of a galaxy, which requires point your telescope at that galaxy, focus the light down onto the slit of a spectrograph, which splits it up into its component wavelengths, and measure the spectrum. And that's a very slow process. And so even by the 1970s, the number of redshifts was still only a few thousand. But as we're going to explain, that rapidly increased, first with the CFA Redshift Survey, then with 2DF and Sloan, so that we had something like 2 million redshifts by the end of the two surveys in 2005. So what enabled us to do that, and Daniel will shortly explain how Sloan did that, but in the case of 2DF, it was this 2-degree field instrument or facility. This sits on the top end of the telescope, so light from the distant universe comes down through this open sort of annulus here, just a few obstructions that hold the instrument together. It comes down below, reflects off the main primary mirror of the telescope, which is almost 4 meters across, and then is focused back through these corrective optics and onto a metal plate here, in which 400 optical fibers have been placed, carefully placed at the positions of the 400 galaxies in that field of view, such that you can pick off the light and take it of each one and take it back to a spectrograph. At the same time, there's another set of 400 fibers that sit up here, and a little robot repositions those ready for the next field. And when you're ready for the next field, this barrel-shaped region tumbles like this, and the new set of fibers move into the focal plane, ready for the next set of observations. There are 400 fibers. It takes about an hour to get sufficient light through the fibers to get a good spectrum, so you can measure 400 spectra an hour this way, and that's what enabled the 2DF survey to build up such a large survey quickly. A few people deserve mention here, where we show some nice pictures of the telescope. So this is the real 2DF. Down here is the mirror, but it's covered by a shutter in this picture. So this was funded by the Anglo-Australian Observatory around 1990, which Michael Rowan Robinson was a leader in pushing this through. It was strongly supported by future directors of the Anglo-Australian Observatory. So putting an instrument of such complexity together, not requires design, but a commissioning team who can sort out the programming of electronics, and that involves astronomers and engineers, and very many people involve. A lot of thanks for getting everything working so quickly. Here's a zoom in of the, so here's the top end, the mirror of the telescope's down here. Here's the robot. This is the focal plate on which it moves the fibers, which come in from the side. If we zoom in, we see each fiber has a little magnet on it that holds it to the metal plate when the robot lets go. And then on the end, it has a little prism, which takes the light that comes down and then takes it off down the fiber. Now, is this going to work? So we now have a little movie of this in action. I like that it says OK. Play and... Okay, so hopefully that will go away. Yes, so here you see the robot in action, moving those fibers, while the mirror down here is collecting light and sending it up to the other end of the telescope. But it would if it was in the dark. You don't really observe with all the lights on like this. So the robot is speeded up here so this movie doesn't get too boring. It didn't quite work that fast. And then you see the size of this telescope as it is maneuvered ready for observations, where it has to point out through the dome so it can see the night sky. The Anglo-Australian telescope is really over-engineered. It wasn't designed for this, but it's built so sturdily that you could put a 2-ton instrument on the top here without there being any flexure as you move around the sky. It's an incredible instrument. And there we go. So then you observe the night sky and measure your redshifts. So back on PowerPoint. Lovely. So that was what was used. And now my clicker has stopped working. There we go. So we then took the other input you need for that is a galaxy survey of galaxies on the sky, and this is the 2DF survey, which was largely down to Steve Maddox and his supervisor, George Estathiou. So this actually took photographic plates that were taken by the UK Schmidt telescope in the 80s and digitized them, calibrated and produced this 2-dimensional survey. And then those were the objects that were targeted using the 2DF spectrograph. We did 2 strips, one in that region you just saw and another strip in the northern hemisphere. The galaxies aren't nicely distributed such that 400 fall in each 2-degree field, so you have to work out how to overlap these fields and then how to assign galaxies to fibers such that the robot doesn't tie all that fiber optic spaghetti into knots. and Gavin Dalton was responsible for a lot of that. You get spectra that look like this for each of your 250,000 galaxies, and you have to measure the redshifts from that. And so automated code that Will Sutherland helped develop does some cross-correlation technique to predict the redshift, and then it shows to the observer what the spectrum looks like along with the emission lines and absorption lines tagged as to where they should be if it's got the redshift correct. And so the observer looks at that and gives it a quality control as to whether it's got the right redshift and so on. There were about 30 people in the 2DF survey. It was an Anglo-Australian collaboration. Here are most of the people in the survey, I believe. There were always some people who came in at various times, and there doesn't seem to be a definitive list of who was in the survey. But essentially, these 30 people were the main movers. The 2DF survey not only looked at baryonic acoustic oscillations and redshift-based distortions. In fact, it had an impact on a whole range of topics in astronomy. There were 100 papers that can be found on the preprint database. 40 of these are by team members, and they cover everything from working out the statistical properties of radio galaxies, putting constraints on the masses of a neutrino. And this was the survey we produced of 250,000 galaxies over the 3 or 4 years that it took to measure the redshifts and map out this diagram. We're going to show you in the later section how we analyze that survey to constrain baryonic acoustic oscillations. And I'll now switch over to Daniel, who's going to tell you more about the use of the Sloan survey in gathering its data.
Okay, is this mic live? I think it is. All right, so I'm very happy to tell you about the SDSS, Sloan Digital Sky Survey. So this is the world's largest Galaxy Redshift Survey. Unlike the 2-degree field survey where they started from photographic plates, the SDSS wanted to take a digital picture of the sky. So basically we're going to map the sky using a large CCD camera. This ended up covering 5 different band passes and cataloging 500 million objects across the sky. And we then wanted to perform spectroscopy to turn that 2-dimensional map into a 3-dimensional map. And we performed spectroscopy in the end of about 4 million objects, most of which are galaxies, but there's a lot of stars and quasars as well. The project started in 1990 and had to build this telescope in New Mexico. So it began taking data in 1998. And we're now completing the 3rd epoch of the survey this year. We actually finished it 2 months ago here in 2014. So this is a 25-year project. We've been well supported from the Sloan Foundation, Department of Energy, NSF, over 50 member institutions. Lots of different groups have come together to make this happen. So just to give you a bit of a slideshow, this is a telescope, the telescope in New Mexico. It's a 2.5-meter telescope dedicated to the facility. What you actually see here is the wind baffle that keeps the wind from shaking the telescope. You can see that unlike many telescopes, this one doesn't sit inside of a dome. There's actually a shed, a garage that rolls off the telescope at night and protects it during the day. The imaging has been really very high impact. This is just sort of showing some interesting points on the sky. This is, of course, the Whirlpool Galaxy M51. Here's a globular cluster in our own galaxy, M13. There's a nice pair of interacting galaxies. So really, we observe the whole sky. So everything falls in. You get to study all different types of objects. Here's a galaxy cluster. Okay, so when the images were all put together, this was the picture of the sky having removed the light from all the stars. So this is taking away all the stars and only showing you the light from the galaxies. And like the previous photographic plate picture, you can see the large-scale structure actually even in the 2-dimensional image. This is the picture of the North Galactic Cap. So this is looking up out of the galaxy in the direction of our North Pole. Here's the South Galactic Cap, or the portion that we could observe from that. And in total, the survey has covered about 1/3 of the sky. And all that data was released to the public in various stages, but it was all finished by January 2010. What's not shown in that picture is the tremendous amount of detail that's actually available in these images. So if you take a part of this image and zoom into there, and then you zoom in again, and then you zoom in again, you can see all the detail. So in detail, this is actually over 1 trillion multicolor pixels on the sky. So there's really a very large amount of data in this. But we now want to go into the third dimension, and that means measuring redshifts. So we want to take spectra and measure redshifts, and we do this with a slightly different technology. Again, it's still based on fiber optics, but we're instead using plug plates. And so what that means is that each of these, this is a plate down here, and I brought one so you can see it. So we'll pass this around. But every hole in here is the location of a galaxy. Basically, this plate will sit at the focus of the telescope. If you covered the plate with film, it would make an image of the sky. And we then, from our previous images, we figure out what spots on this image are interesting because they contain galaxies or quasars or whatnot. And we're then going to drill a hole at that location. We plug in these fibers. So this is a time-lapse movie of somebody plugging the fibers. All these 4 million fibers have been plugged by hand over the past 15 years. So it takes about an hour. We have 9, at any given night, we'll have 9 of these plates ready to go. So basically, when you observe the plate for an hour, you take it off the telescope, and you put another plate on and continue observing. This plate only gets used once because the holes are drilled for the locations of that particular spot on the sky. So I'll pass this around. I want to warn you, it's pretty heavy. You cannot hurt it. You cannot hurt it, so don't worry. But you can hurt the head of the person in front of you. So please be careful. It's pretty big and heavy. And I'm happy to answer questions about it, but maybe after the full seminar. So SDSS has operated in various phases. The SDSS 1 and 2 survey was producing a detailed map of about 20% of the sky out to a distance of 2 billion light years, with additional coverage out to 4.5 billion light years. And this is really one of the most productive astronomical surveys ever. We've had several thousand refereed publications based on SDSS data, and really spanning all different areas of astronomy. It's actually hard to think of an area of astronomy that hasn't had some interesting impact from SDSS. We then switched to SDSS 3. SDSS 3 is the project that I've been director of since actually about 2006, but we started operating in 2008 for 6 years. There's 4 surveys inside of SDSS 3. There were 2 surveys that were actually working on the Milky Way galaxy, another survey which was looking for planets around nearby stars. But the survey that's relevant to the topic here is the Baryon Oscillation Spectroscopic Survey, which is the largest survey yet for large-scale structure, including 1.5 million galaxies, stretching out to 6 billion light years over 25% of the sky. So this amounts to a 7-fold increase over the SDSS 1 and 2 survey. So this is going to be a fly-through of the survey. This is about 20% of the area. So you should imagine that what you're seeing here is some big chunk of the sky, 20% of the sky, 20% of the survey, so about 4% of the sky, 5% of the sky. And what you're going to see now is we're going to start with a little slab right here, and this slab is going to move out. So basically, we're going to fly out through the survey. As we fly out, you'll see galaxies come and go, and the galaxies will appear as light red, and then will turn to black, and then we'll turn back to red, so you get some sense of the motion as we go through the survey. We're going to hit go here. The circle is a radius of 500 million light years, which will be an important scale later on. And just it shrinks in size because as you look at things further and further away, it's going to be a smaller and smaller angle on the sky. And you can see the large-scale structure. You're basically flying through the cosmic web. We're now at redshifts of order 0.4, so about 4 billion light years from us. And it's getting, the survey gets denser and denser out in these parts. We put a lot of effort into observing galaxies around redshift of 0.5. So you can sort of see the cosmic web waving backwards and forwards as we zoom out. So this is 20% of the data in the survey. SDSS is a big collaboration. We've had really a tremendous level of dedication of all of the members over many, many years. It really does amount to hundreds of people, too many to really list, except that I did actually try. So there's there's 200 people who have reached a particular level of threshold level in the survey, and really, honestly, many hundreds more who have used the survey data in some way to try to contribute their science ideas. But it's really much more. I'm sure the 2DF folks would say the same. These collaborations are much more than just a big data collection project. It becomes its own scientific community. It's really a lot of our closest colleagues. And it's an opportunity for us to blend together the expertise of many different subfields, and it becomes a very close-knit collaboration with approaches to hardware, data reduction, data releases, public outreach, science applications. It becomes its own life, and one that I think we've all really appreciated. So I'm very happy to say that SDSS 4 is starting up now and will be running until the late part of this decade. And at this point, I think Sean and I will take a pause here for just a couple of minutes to answer any questions that have come up from this first part, and then we'll get on to the more of the aspects of the interpretation of large-scale structure. So questions, please. Yeah.
So the graphic before the talk started characterized kind of like a drop falling into a pool, say a swimming pool, which seemed to be very smooth fluctuations. These fluctuations seem a lot more sharp. How do you characterize that they're really from oscillations from the very smallest?
Well, we'll certainly get into more of that in the next part, but you're seeing the structure on relatively smaller scales. When you go out to large scales, the universe is actually substantially more homogeneous. So the fluctuations that are on these large scales are only at the level of 5 to 10%. And then we still can describe things as small enough in the context of these ripple ideas that we'll get to later.
I have a question about redshifts. So if my intuition is correct, I guess some galaxies should be moving with our galaxy, and some of them should be moving in the opposite direction, assuming it's not in the point of observation is not in the center of the expansion. I'm not sure if this is the case, but if we're moving away from a ball, is there like a place that we can show as the origin of the expansion, or is it a much different case than that?
Yeah, well, why don't you...
The analogy of the expanding ball, that wherever you are on there, you see other points around you moving away. There is no center of the expansion, or everywhere is the center. So there isn't one place that the explosion happened. The explosion happened in the whole of space, and it's this analogy with that ball that helps you understand that there's no actual center. Everything is expanding away from everything else.
Thank you.
Or another way of saying it is that every observer thinks that they're at the center of the expansion, and therefore nobody is special. Okay, well, let's turn it over to John. Next part here.
So we've heard how we map the universe and produce these fantastic images of the distribution of light over colossal scales, of which we're part. Now what I want to do is to talk about how we process this information down and use it for quantitative purposes to learn specific things about the universe. But let's just recap. The large-scale structure of the universe has been known about for many decades, going back. Indeed, Hubble was, I think, the first to demonstrate that galaxies were not uniformly distributed on the sky. So even with old photographic plates, we learned something about this. And this picture was produced actually in the 1940s. It took two astronomers 10 years staring at photographic plates with an eyepiece, counting galaxies one by one to make this picture. So we think we work hard today if we spend a few hours on our laptops writing software, but the dedication of the old generation that each successive generation builds on is always impressive and humbling. So what we've had to do is to take such pictures, to take at least part of that, and the pictures that you see in, say, the 2DF survey or the Sloan slices are exactly that, a small strip on the sky that you expand in the radial direction with spectroscopy. So if you like, cutting out a kind of pizza slice through the universe. Sean showed you that before. There it is in different colors. Let's just emphasize that every single dot here is an individual galaxy like the Milky Way. And it's not that there are no galaxies at great distances. We simply observe all galaxies down to a certain apparent brightness. And out here, they have to be particularly luminous to be seen at all. So what do we do with this information? Okay, there's just one point I wanted to make that I think is quite important about this, that frequently when you give talks about cosmology and the modern picture, dark energy and so on, people say, well, hundreds of years ago, everyone thought that the universe was a plate sitting on the back of a turtle. We laugh at them now. So isn't the ideas that we're hearing today just more of the same nonsense that will eventually die away? Well, I don't think so, because eventually technology reveals to us sufficient of the universe. So, for example, in this slice, you see here the distribution of galaxies seen in the northern hemisphere, here in the southern hemisphere. Can you tell the difference? Well, obviously not identical, because features in different places, but their character is the same. So I think we can look at pictures like this and see that we have what we would call a fair sample of the universe. And therefore, we can be confident if we looked in here, we'd see more of the same kind of thing. So we want to now proceed to analyze that thing quantitatively. And it's really only like this, that once upon a time, you could look in books of maps and find this thing, and some of you may have no idea what it is, but as the data improve, it becomes clear. And then eventually, the picture never changes because the data have improved to a critical point. Okay, so this is the sort of thing that we have to do. Imagine that you take a journey through space, traveling along a line. Around you, you would see the density of matter or light fluctuating up and down around some mean. Rho is the density. So for convenience, let's say the density we observe is the global average in the universe times 1 plus some little fluctuation, which can be positive or negative. And this has the character of noise. Now, anybody who's ever had a bad telephone conversation or watched a television that wasn't quite well tuned in knows what I mean when I say noise. And here is an illustration of this sort of thing. There's a signal in there, but there's random fluctuations that are almost hiding it. So the mathematical tools for dealing with this sort of process were in place from the early days of telephone systems. And we use them in cosmology. But with one critical difference, which is that there is no signal, or rather, what we're studying is purely the fluctuations. That is, the fluctuating density of galaxies in the universe is the process that we're interested in. And we can characterize it statistically. And the way to think about this is we use a mathematical tool called Fourier analysis, where you start off by saying, what's the simplest sort of fluctuation I can imagine? And that's something that just oscillates, just like waves on the surface of the water. High density, low density, high density, low density, with the crests running in a given direction. What you can imagine is adding together a number of such waves. And frequently one sees this, of course, on the surface of a swimming pool. So here I've taken different waves running in different directions and added them together, and you get a pretty interference pattern, where sometimes the troughs coincide or the peaks. But we don't see this sort of regularity in the galaxy distribution. What we see is something much more like this. And all I've done here is taken the same waves there, but moved each one by some random amount in its direction of propagation. And that means technically, we've given each one a random phase. And now suddenly, you see there's no structure, and yet there is structure. And this is a very simple model that has some analogy to the kind of fluctuations we're seeing in the distribution of light in the universe. So mathematically, and we don't need the equations, but it helps professional astronomers remember the words they have to say. The fluctuating density disturbance is the sum of some amplitude times a function that represents a particular wave, summed over lots of different waves. This number k is what we call the wave number. It tells us the scale, because when we look at the galaxy distribution, we clearly see fluctuations of different scales. There are things that are hundreds of millions of light years across, things that are only millions of light years across. Here, we would have waves that fluctuated much more rapidly. They would have a different wavelength, and this number k, the wave number, is 2 pi divided by the wavelength. So there'll be lots of k's shortly in the next slides. So I've said, but therefore, that the phase of these waves is irrelevant, but their amplitudes is very interesting. We want to know how big the excursions in densities corresponding to each mode is. And there's a simple relation that comes from this, that if you want to know the average value of the square of the fluctuation in the density, you simply add up the modulus squared of the wave amplitudes. And this is a thing that's called the power spectrum. This is a central quantity in these sort of analyses. I'll often show it in this form, big delta squared, and all that means is the contribution to the power, the contribution to the variance in the density that comes from a given range of modes. And these are modes that live in a fixed bin of logarithmic wave number, so basically a factor of 2 and a bit in scale. So I'll show you a plot of what this actually looks like in a second. But let me first of all mention there's another statistic that we have to use that you'll also see plots of, which is the evil twin brother of the power spectrum. And this is called the correlation function. So what you should imagine here is that you take the fluctuating density field, you make a copy of it, but you move it along by some offset called r. You multiply the two together, and the angle brackets say you take the average. So if r is small, you're just measuring the overall variance in the density. If r is very large, the two copies don't really know anything about each other. The positives and negatives in one will, on average, cancel the positive and negatives in the other. So at large separations, this correlation tends to 0. And it's how it tends to 0 is the interesting thing. From the point of view of galaxies, it's the best way of thinking about it is it's an excess probability over random of finding a neighbor. So if I sit on a galaxy like the Milky Way, if I go about 10 megaparsecs away, I know that actually this correlation amplitude is about 1, which means I'm twice as likely to find a neighboring galaxy as if I just picked a point in space at random. Alternatively, if you imagine filling up the universe just with clumps of matter, each one put down at random, and these clumps are about big L across, then the correlation function would be big for separations less than L and then falls to 0, whereas the power spectrum, it would be small where the wave number is less than 1 over L. So wave numbers are like inverse lengths. Okay, enough. Let's show what it actually looks like. Here is the power spectrum that one deduces from the 2DF Galaxy Survey. So up the side, I've got the power in this form of the fractional variance in the density of galaxies in a given range of scales. And here is the wave number. So 1 is an interesting point here. Because here, what you're saying is different regions of space differ in density by a factor of roundabout of order unity. And we can read off which wave number that corresponds to from the data points. And it comes out to be a wave number a little bit bigger than 0.1. So that corresponds to a wavelength of 60 megaparsecs. So broadly speaking, that tells you 100 megaparsecs and above are clean wavelengths in the universe. That is, the density is perturbed only by a small fraction. And theoretically, those sort of scales, which you call linear scales, are much easier to analyze. Now, the data that you see here are compared with some smooth lines. And these are theoretical models. I'll just tell you what they say, and then I'll give you an argument to try to motivate why the theory has the appearance that it does. There are two things being varied here. The lines at the bottom are basically those characteristic of a low-density universe. And the density of the universe is measured in terms of a quantity called omega. Sean mentioned omega. Did everybody notice that? Okay. Omega, yes, the critical density of the universe, just a few atoms per cubic meter. It's enough, apart from anything else, to curve space-time around in itself, so the universe becomes closed in a finite volume. So it's very important for us to know whether omega is less than 1 or bigger than 1. So a low-density universe puts the theory down here. A high-density universe puts the theory up there. And you can see that we can read off the density of the universe if you believe the theory is correct. So somewhere in between corresponds to a density parameter of about 0.2. So that's a universe that's well below critical density. Unfortunately, the observations are actually sensitive also to the value of the Hubble constant. And we often see our graphs full of this number little h, which is the Hubble constant in units of 100 kilometers a second per megaparsec. And modern values of this are somewhere around 70 kilometers a second per megaparsec. So we can infer that the density of the universe is about a third of the critical, therefore. But the interesting thing that you have to look more closely to see is that there's two sets of lines in here. The red ones are a universe that contains only dark matter. I'll say a little bit more about what dark matter may or may not be in a second. The others contain also ordinary material. It's called baryonic material in the trade. All it means is ordinary stuff, like this desk, like my head. And this is set at a fraction that we infer from what's called primordial nuclear synthesis, that is, studying nuclear reactions in the early universe to build up the light chemical elements. All of these lines, though, have a relatively small fraction of baryonic material. I'd have to go further down here, much further down, to reach a line where the matter content was purely ordinary baryons. And so when anybody asks me, what evidence do we have the universe contains dark matter? I actually say, this is one of the pieces of evidence, because a universe that contains purely baryons, baryonic material, suffers from pressure whenever it's compressed, and that tries to combat the fact the material is being compacted, and that causes oscillating sound waves. So these are the baryonic acoustic oscillations as we see them in the power spectrum. And the fact is they're a very small effect. So the fact that the power spectrum that we observe is a largely smooth function is actually telling us two things. Its form tells us the density is low. The fact it's smooth tells us the density is mainly made of dark matter. If you wanted other evidence for dark matter, some prettier pictures. Here's gravitational lensing. This foreground galaxy here has a high redshift galaxy behind it, but the light is actually going around the side because light falls under gravity and the image gets stretched out into this arc here. So from that sort of information, we can measure very accurately how much mass exists in that region. Actually, in the 1930s, the American astronomer Zwicky measured the orbital velocities of these individual galaxies around each other, which is also sensitive to the dark matter. In both cases, you find far more mass than you can account for in the starlight that's here, or indeed the gas between the stars. Roughly about 6 times as much matter in total as in the form of normal baryonic material. And it's that factor of 6 is pretty well what we find from analyzing the power spectrum of the galaxy field. So I need to explain to you why it is that the power spectrum knows about the density of the universe. And in short, the answer is because the universe contains not only matter, but also radiation. And this radiation was mentioned briefly before. It's the microwave background, and it's a critical component of modern cosmology. First discovered by accident in the 1960s by these radio astronomers, where we realized that in every direction, we're looking back to a time when the universe had a temperature of a few thousand degrees, sending radiation towards us that's cooled by the expansion just to 2.7 Kelvin. And Sloan showed this idea that the density of radiation rises more rapidly as you go back in the past to higher redshift than ordinary matter, because both radiation and matter are being pushed together, but the radiation is also getting hotter, and that gives that line a greater slope. By the way, dark energy, which will increasingly become the focus of this talk, is the other component of the universe, which turns out to be the dominant one, is, as far as we can tell, independent of time and its density. So it was unimportant at early times, is the dominant quantity now. Anyway, the point is that this matter radiation era was one of the critical times in the universe. And that's because the radiation can influence the growth of structure. Sloan showed in some of the numerical simulations, we believe the large-scale structure in the galaxy distribution is formed by gravity just pulling more and more matter together. But that gravity is generated both by matter and by radiation. Radiation has energy, it has weight. But of course, radiation moves. And so in the early universe, matter and radiation can separate. And they can separate on scales up to what we call the horizon. That is the speed of light, c, times the age of the universe at that time. So since the microwave background was generated at t of about 400,000 years, 400,000 light years then expanded to a larger distance now of about 300 million light years is the horizon size. So on smaller scales than this, the radiation has leaked out of the matter, and therefore it's not present to add its gravity to pulling the matter together, and therefore the growth in matter fluctuations ceases. So we can see from this simple argument that what we're really interested in is the horizon size at the epoch of matter-radiation equality. And that point depends on the matter density. Here's the density versus time. The radiation is doing this, the matter's doing this, but how much matter is there? If we have a low matter density, then the point of crossover happens at a later time, and therefore the horizon scale is larger. So it's this change of the horizon scale with the matter density that gives the density dependence in the power spectrum. Okay. Now I want to shift to a different aspect of structure formation, which is the redshift space distortions. So these arise because if you're going to have fluctuating density of material in the universe, you must have material that's moving. So here's a slice from a numerical simulation taken at relatively high redshift when the universe is a quarter of its present size, redshift 3. Let's step it forward. Look at the material around this low density region. What it's going to do is it's going to flow out onto this supercluster filament here. Okay, I hope you're convinced by that the only way to pull matter together is to have matter falling into it. So there's some additional velocity. Now remember, what we measure with galaxy spectroscopy is the redshift. It simply tells us how fast is that galaxy moving relative to us. And that's a combination of the velocity from the expansion of the universe and this so-called peculiar velocity. So these peculiar velocities were known actually right from the start. In 1912, the very first galaxy redshift measurement was made by Slipher in Arizona, except it wasn't a redshift. It was actually a blue shift. So the nearest galaxy to us, M31, is actually coming towards us rather than going away as it should be in the uniform expansion. But it wasn't until the mid-1980s that it was actually figured out what this did statistically. And the person who figured it out was someone I'm happy to say is a very good friend of mine, as well as a great scientist and colleague, Nick Kaiser. And he wrote a paper, the sort of face that launched 1,000 ships in cosmology terms, with this picture in it. So suppose I have an increase in density around some location with shells of matter that have fallen in. Each of these shells is heading towards the radius. So if you're over here, you look at this point using redshift as a distance indicator and Hubble's law. Instead of placing these shells at their correct distance, because they're falling this way, they have a lower redshift than they should have, and you put them closer in. So things tend to flatten. And actually, those velocities can even turn the whole structure inside out if you use a radial coordinate that just comes from the redshift. So this sounds horrible, but it actually turned out to be useful because these velocities are interesting. Why are they interesting? Because they can measure the density of the universe in a different way. So here's a nice movie to show what would happen as you flip from a simulated distribution of matter seen with a genuine radial coordinate to one that's seen in redshift space. Here's real space. Here's redshift space. I guess it's obvious that the observer is placed here. So everything is stretched out or moved along the line of sight. And you can see two effects, actually. First of all, whole supercluster filaments are bodily moving, so they're being transported in space. But also, very dense clumps of matter here are actually stretched out. And this effect is called the finger of God, for obvious reasons. And it just says that here you have galaxies that are orbiting around each other. And where you've got to on the orbit dictates whether the redshift space distortion is towards you or away from you. So this is what it would do for something like the 2DF survey. Here's a simulation of how the 2DF should look with purely exact radial coordinates. And now we turn on the redshift space distortions. This looks much more like the real thing. And the point is we can measure that difference. And we do it using the correlation function. So I talked about the correlation function as counting an excess probability of finding a neighbor. So you are here, you look at a given galaxy, you say there's a galaxy a distance r away. How much more likely is it to find a neighbor over here compared to random? But now we have to do this as a function of the radial separation and the transverse separation, because the radial separation gets wrecked, or at least systematically changed, by peculiar velocities. The transverse separation doesn't. And you can see both these effects in this plot from our 2001 analysis, which really I think was the first time we had enough signal to noise to see all this going on clearly. So here's the transverse separation, here's the radial separation. There's a fancy color scheme that encodes the amplitude of the clustering, which becomes larger towards small separations of pairs. At large transverse separations, you see the contours are flattened, and that's the systematic infall onto superclusters. At small separations, you see the stretching along the line of sight, the fingers of God. There's no time here to go into the technical details of how we translate this amount of flattening into a measure of the density of the universe, but clearly the denser the universe is, the larger the velocities produced by gravity, and the greater this flattening. So by 2001, the 2DF had produced two distinct measures for the density of the universe. One from the power spectrum, one from redshift space distortions, and they both had a precision of 20 or 25%. And they're both indicating a density of about a little under 30% of the critical density. The best by modern value is actually almost exactly 0.3, and the precision with which we know that today is somewhere around 5%. So that picture of cosmology is now stabilized. None of this says anything at all about dark energy and the accelerating universe, because everything I've talked about is the component of matter in the universe that can clump together. But it's possible that there's a component that extends uniformly throughout space and doesn't clump. And indeed, we know that this is the case. So we'll be talking about the numbers of different ways in which we know this. But let me start off with historically, the first time this argument was made, which is using the microwave background to look at the additional curvature of space that's produced by a uniform component. So the microwave background at a certain level of detail is very uniform. If you look at the sky, the same radiation intensity comes in all directions. But if you stretch this picture and you measure very precisely, you see this. And this picture was really only fully revealed to us about 10 years ago by NASA's WMAP satellite. And here what you see are regions where the temperature is slightly higher than average or slightly lower than average by of order 1 part in 100,000. This is an amazing picture. I mean, I never tire of staring at this and thinking that throughout human history, this has been on the sky waiting to be seen, and we're the first generation to see it. And it's the same point about having sufficient maps of the large-scale structure of the universe to know that you've seen the characteristics of everything there is. And these are the initial conditions for large-scale structure. These small fluctuations will be acted on by gravity from 400,000 years to the present day to make the complex structures that we see in the galaxy maps. But what's interesting is that the nature of that picture would depend on the curvature of space. And in short, if you lived in a closed universe, one with a very high density, then that acts to magnify the pattern. And these blobs on the microwave sky would be beamed up to something of this size. If we lived in a universe of well below critical density, they'd be moved to very small scales. And it's actually rather easy to see in outline how this would work. So let's think about the analogy that we saw in Sean's initial segment of a two-dimensional sphere as a lower dimensional analog for the universe. And in that case, just lines on the surface of the Earth are like light rays. So let's say I stand on the North Pole and I send out a couple of light rays, perhaps even in opposite directions, just straight lines going along the surface of the Earth. Eventually, those will reconverge at the South Pole. Right? Those two great circles will meet again. And in a high-density, closed universe, that's exactly what happens to light rays. They get brought back together at large distances. So did we see this? Well, in 1997, actually the last time I was in Hong Kong, this is what the state of data on the microwave sky looked like. This is the microwave power spectrum, so this is the squared variation in the temperature. And now this is angular wave number, so small angular scales are here, large angular scales are here, about 1 degree is in the middle. And there were two models on the market at that time. There was the one, they both already favored a density parameter of somewhere around 0.3. One of them contained nothing else. The other contained a majority shareholding of about 0.7 of an energy density of the vacuum. So that's the red line. And it's hard to tell the difference at that time, although I'll point out that even then, there were upper limits. Nobody had detected very well these fluctuations on small scales, but they were clearly not present. And the blue line was in difficulty. So as the data got better, you'll see the red line was verified. So this is the modern vacuum-dominated universe that we live in. And that favors, therefore, a universe without any curvature. Whereas if there was only matter, it would be the blue line. And that blue line was already ruled out by the lack of small-scale CMB data. All these arguments were made in a very prescient paper, even back in 1990, that a cosmological constant, as it was called then, an energy density of the vacuum, dark energy, these all things all mean roughly the same thing, had to be present. And yet somehow, people weren't paying attention. Even this fellow. He was lecturing in a summer school for graduate students in 1996. And we were asked to vote on the value of the cosmological parameters. This line represented the energy density of the vacuum, and with one exception, which wasn't me, everyone thought it had to be 0. But actually, the evidence from the microwave background limiting curvature of space and the arguments for low space density, which the large-scale structure refined subsequently, were already there. And so when the supernovae came along in the late 1990s, with arguments from the apparent brightness of supernovae versus redshift, the ground was already prepared for people to have arguments that favored an energy density at the vacuum. And without that, I think the supernova results wouldn't have met with their instant acceptance. So this is the picture that this has led us to, which you might well call the implausible universe. As far as we can tell, to about 1% precision, the total energy density is the critical value. About 70% is in the form of a uniform component that doesn't cluster. The remainder is largely dark matter, and only a few percent of also atomic material. Okay, so that's the end of this segment. We're now going to zoom in a little bit on this issue of the baryonic acoustic oscillations.
Okay, thank you, John. So I think I can be quite brief. So we've early heard that the universe undergoes a transition when it's about 400,000 years old from being ionized to being neutral, which is important because here the photons are trapped and scatter off the charged particles in the plasma, whereas here they freely stream and they don't interact with neutral matter. So here, those photons, which for most of the time dominate the energy density in the universe, create a very high pressure in the plasma. So if you have an overdense region, not only is it overdense, it's overpressured. And so you have an overdense region, the pressure acts against that and makes it want to expand. And so the baryons, perturbations in the baryons, oscillate as sound waves. Up until 400,000 years after the Big Bang, then the photons just escape, the baryons don't feel their pressure anymore, and the sound waves stop propagating. These are the waves you see in the microwave background that John has explained, and one can work out what angular scale they're on. It basically corresponds to how far those sound waves can propagate since the Big Bang until this recombination time. I don't think I'll attempt to show this movie, but one way to understand how these baryonic acoustic oscillations give us an observable signature in the galaxy formation is to consider how different wavelength perturbations evolve. So there are two components to the density fluctuations. There's the baryons, and then there's the dark matter. And the dark matter doesn't interact with photons. That's why we call it dark. We can't see it. It's not visible. And so they don't feel the pressure. And so an overdense region in the dark matter won't feel the pressure, and it will just grow under gravity to become more overdense, whereas the baryonic parts will oscillate. But they can't oscillate on arbitrary large scales because what we call the sound horizon time, the distance that sound can travel since the Big Bang, that starts off very small and grows with time. And so to start with, it's only the short wavelength perturbations that can oscillate, and then as time goes on, it's the larger ones. And so what happens is that the perturbations in the dark matter and the baryons get out of phase. Okay, so they grow under gravity, but they get out of phase. And depending on what wavelength you're looking at, they can either get back into phase, as in this case, we've got the baryonic and dark matter components adding up to quite, out of phase in this case. The baryonic and dark matter components are out of phase, and so the perturbations overall are slightly less than in the dark matter. Whereas here, they might have oscillated more times and come back into phase, and so the perturbations are slightly higher than just those in the dark matter. And so whether they reinforce or whether they cancel out is a function of wavelength. And John has also already shown a picture. His power spectrum, this is the same sort of thing, but this one is multiplied by k cubed, so it's sort of tilted over. So as you go from large scales to smaller scales as a function of wave number, you see these oscillations, which are due to the baryon and the dark matter components getting in and out of phase. And it's the total mass perturbation which grows under gravity after recombination and seeds the structure where all the galaxies form. So when we trace the galaxy population today, 13 billion years after those baryonic acoustic oscillations happened, we're sensitive to this total overall fluctuation. And if the baryonic fraction were extremely small, it wouldn't make much difference and we would just see this smooth spectrum. The baryon fraction's larger, we see larger oscillations. John has shown you some of that. And that's what we want to measure with the 2DF survey. So a lot of the work in actually doing this is modeling the survey. So we want to look at perturbations. We don't want to look at just the number density of galaxies. We want to see how they differ from what you would expect if there were no fluctuations. If galaxies were just randomly distributed. So here are the redshift distributions in the southern, northern, and the random fields that were also observed in 2DF. And there are lots of fluctuations in density as a function of redshift. So there's just a number of galaxies in different redshift bins. In order to know the random density, the smooth density to measure the perturbations, you have to model what number redshift distribution you would expect. And we do that by modeling the luminosity function of the galaxies, how many bright galaxies there are, how many faint ones. As John explained, at high redshift, we only see the very bright ones. At low redshift, we see faint ones as well, but there's not as much volume here. So this falls off here because you don't have much volume. This falls off here because there aren't bright enough galaxies. And so we have to model that. We also have complications that the original survey area isn't surveyed to the same depth in each direction, and so we have to model how this random count varies because of that on the sky. Then we have to model the fact that we don't measure redshifts for absolutely everything, and so we see this 2-degree field pattern coming in. But once we've done all that and we can test that we've done it robustly, we can measure this power spectrum. And that's what we did in 2005 with the 2DF. And what we saw is the power spectrum isn't quite smooth. There are these oscillations due to baryonic acoustic oscillations. The theoretical model, if you had an infinitely large survey, would be this blue cyan line, taking into account the fact that the survey is finite. You have these problems of Fourier space. When you multiply two functions in real space, then you convolve them in Fourier space, and that reduces the amplitude of the oscillations. If we measure that, then, as John has already said, we get constraints on the baryon fraction because we can see how large those oscillations are. And this is the work we did with Will Percival. And also from the overall shape or curvature of the spectrum, we get constraints on the mass density, overall mass density in the universe. And so this was this combination of plots were the money plots from our work in 2005, detecting the baryonic acoustic oscillations and getting a clear measurement that there are baryons in the universe. Of course, we knew that, we're here, but this is the cosmological average density of baryons in the whole universe. I'll move on to Daniel, who explained similar things in Sloan.
Okay, so I'm now going to tell you about the baryonic acoustic oscillations from a slightly different vantage point, which I think will hopefully be complementary. So here we want to consider how the universe responds if you start off with some little region of the universe that's overdense. So you have an initial overdensity. It's overdense in dark matter, it's overdense in gas, it's overdense in neutrinos, and it's overdense in photons. And because it's overdense in photons, it's also overpressured. And just like if I had a balloon in this room and I popped it, it would emit the evolution of the universe that causes that overpressure to try to spread out as a spherical sound wave. That wave will travel outwards at the speed of sound, which at these early times is fantastically high. It's actually 57% of the speed of light. And the wave will travel until you get to this epoch of recombination, 400,000 years after the Big Bang. At that point, the universe becomes neutral. The photons will separate from the gas, and that causes the sound wave in the gas to stall at a particular radius. So the wave will actually stall at a radius that's 150 megaparsecs, about 500 million light years more than the original, away from the origin. And now you have the situation that the gas at the center and the gas in this ring will both preferentially seed the formation of galaxies. And so you find that you predict that galaxies should have a preferred separation of 150 megaparsecs, about 500 million light years. So if I have one galaxy here, I'm slightly more likely to find another galaxy 500 million light years away. So I'll now just show you this again, but with an animation of the actual codes, where this is now going to be radius in co-moving units, so units that are expanding with the universe. And we'll have the mass profile, and I've got dark matter, gas, photons, and neutrinos all starting off with some overdensity at the center, and now we'll see how this evolves over time. If I can get this to work. So I've let the movie run forward. We have the dark matter staying at the center. We have the gas and the photons locked together because of the plasma effects. And they're traveling outwards. And the neutrinos are also traveling outwards. And now we will go out to the epoch of recombination. So we've reached recombination. The photons are beginning to separate away from the gas. And now the gas will tend to stall at this location as the photons smooth themselves out. And now the gas will try to attract dark matter. The dark matter will try to attract gas by gravity, and things will come back into lockstep as we get to low redshift. So now we'll preferentially form galaxies here, preferentially form galaxies here, and this is this characteristic distance of 150 megaparsecs. Now, unfortunately, we don't get to see little bullseye patterns in our data sets. We don't get to see these little rings because the universe has actually been perturbed at all locations. I described the response of a perturbation at a single location. Instead, the universe has been perturbed everywhere. Every region has emitted a little sound wave that causes an echo 150 megaparsecs away. So we resort to signal processing techniques to try to analyze this. And the one that I focus on is the galaxy correlation function, which you can think of as sitting at a particular location and counting the number of galaxies in a shell at a given radius, and repeating this as a function of the radius, and then repeating that around all possible galaxies in the survey. So that's the correlation function. We're basically just trying to calculate how many pairs there are in the survey compared to the number we expected from a random distribution. And so this led to the result in 2005 of this excess bump in the correlation function at 150 megaparsecs, 100 H inverse megaparsecs. Remember, this H is about 0.7, so H inverse is about 1.5. So this was the result from SDSS, that we were finding this characteristic bump called the acoustic peak. And the position of the peak, the relative position in a left-right sense, allows us to measure, to infer the distance to this set of galaxies. So if I tell you that I'm 6 feet tall, all you need to do is pull out your protractor and figure out from the angle how far away I am from you. In the same way here, if I tell you that this characteristic scale in the galaxies is 150 megaparsecs, if you do the analysis with the wrong distance, you will get those. If you sort of say, oh, all my galaxies are a factor of 2 closer, you will infer that distance to be too small. If you instead say the galaxies are a factor 2 larger, the distance will be too large. If you get the distance just right, then you'll find the bump at 150 megaparsecs. So this allowed us to measure, as I say, the distance to redshift of 0.35, and also the matter density of the universe, coming up with values that I think still bear out today. So that first measurement from SDSS gave us a 4% measurement of distance, and now we've been marching on. So the analysis of the final SDSS2 sample, led by Will Percival, gave us a 2.7% distance. And that takes us to SDSS3. So I'll show you the results that have come from the latest samples released earlier this year from SDSS3. This is from about 8,500 square degrees of the survey, about 20% of the sky, using 1 million galaxies. And we'll have the full data set, the last 20% of the sample, available later this year. But the key result now is this acoustic peak that we find at very strong significance. We've now managed to refine the distance from this method to 1%. So we're now getting a very beautiful peak here. If you prefer to see it in power spectra, here's the wiggles now in the modern power spectra. So the data's gotten very, very pretty. This is the result at redshift 0.57. We also analyzed a lower redshift portion of our data at 0.32, again finding a sharp acoustic peak. This one gives about a 2% distance measurement. So in summary, we're actually seeing this acoustic peak in multiple places. We see it in our galaxy distributions at various redshifts. We see it in the microwave background data. So this is great because we're seeing the same fingerprint, the same telltale signs of these sound waves at multiple redshifts. This allows us to demonstrate that we really understand that structure forms gravitationally, that you have this clear progression from the structure that we see in the early universe to the structure today, and we can use it to measure distances as a function of redshift. So this is the plot of distances versus redshift. Here's our data points from SDSS 3. Here's a data point from the 66-degree field galaxy survey, and also the Wigglesy, which is very much the follow-on to the 2DF survey using that same facility with upgrades in Australia. And so this is showing that as you go to higher redshift, that the objects appear to be more distant. Okay, that's good. The remarkable thing is that if you now take the prediction of this from the microwave background data, assuming a universe that contains a cosmological constant and is assumed to be spatially flat, here's the prediction from that. So that's not a fit to the data. That's actually a prediction from the cosmological model, assuming a universe that has no spatial curvature and contains a cosmological constant. So if we now divide out by that best fit line, you come to this data, you can see the percent level agreement between the distances that we measure from the baryon acoustic oscillations and those predicted from the flat cosmological constant model. Now I keep saying the words flat and cosmological because you might prefer to assume something else, and we'd like to see how much sensitivity the data has to ruling those things out. Okay, so first I'm going to talk also then about what we can see. We're actually also looking for the baryon acoustic oscillations in a different phenomena. This is not using galaxies. This is now using the clustering of gas between the galaxies, which is revealed in the spectrum of quasars. As the light from distant quasars travels to us through the intergalactic medium, it is selectively absorbed at the 1 to 2 transition of hydrogen, which is at 121 nanometers. And so every quasar spectrum is actually telling you, is giving you a map of the neutral hydrogen along the line of sight. And one of the big ambitions within SDSS 3 was to try to measure the baryon acoustic oscillations in this data set because it allows us to access much higher redshift. Quasars are very, very luminous. You can see them a long way away. And this method allows us to map out not redshifts of 0.1 or 0.3 or 0.5, but actually out at redshifts of about 2.5. And we were very happy this year to find a strong detection of the baryon acoustic oscillations in these correlations of the Lyman alpha forest. I should say in the context of the plate that's been passed around, how remarkable this is from a technological point of view. So the plate that we're showing you, the telescope is actually, when it focuses the light from a given spot on the sky down onto that fiber, the telescope is selecting a region of the sky which is about 1/100 billionth of the sky. So if the telescope is actually sorting all the light that's coming down to hit the telescope. It's taking 1/100 billionth of that area and focusing it down onto that fiber. So it's a pretty amazing optical precision that's going on to accomplish that level of resolution. The light that's being focused is coming from a quasar on the other side of the universe. That quasar is about 10 million times fainter than what your eye can see, even on a very dark night. So about 1 billion times fainter than what you can see here in Hong Kong, at least in the city center. And we're then taking that light, tiny amounts of light, spreading it out into 1,000 wavelength bins. So everything is being sorted into 1,000 wavelength bins. In a given wavelength band, we might only record about 100 quanta of light, 100 photons coming from that distant quasar. And this effect corresponds to the idea that if I receive 100 photons at a given wavelength from a quasar on one side of that plate, then a quasar on the other side of the plate will have an extra 1/10 of a photon on average at that same wavelength. So that's the effect we're looking for. It's these, just amazing levels of precision to sort out, to take the light from the night sky, sort out the parts that we want, divide it up in wavelength, divide it up in angle, and then notice that there's this extra 0.1 photons coming for every 100 photons of some object several degrees away. All right, well, the reason that we wanted to push high redshift is because at high redshift, you actually should be back in the decelerating era. So we actually now can see that the universe was decelerating from redshift 2 to redshifts of order 1/2, and then starts to accelerate. So we are now seeing that this idea of dark energy, the cosmic acceleration, is only a recent phenomena. We can clearly demonstrate that at intermediate redshifts of order 2, that the universe was decelerating. All right, so what are we trying to get out of this? Well, we'd like to ask the question of whether this dark energy is actually constant. Is the cosmological constant actually constant, or might it vary in time? Cosmologists tend to parameterize this as a parameter called W, where W equals -1 is the cosmological constant, and different values of W correspond to evolution in the dark energy density. Or we might be interested in testing whether the universe is actually flat. As John explained, in general relativity, you can have different spatial curvatures. The universe might be flat like a sheet of paper, or it might be curved into a sphere, or crinkled like a potato chip. The acoustic oscillations generally give just a wonderful way of testing this, because we have this big lever arm out to the, big distance out to the CMB to test this with. And these differences actually make sharp differences in the predictions on the plot I was showing you. So if I instead, this was the prediction for a flat universe with the cosmological constant. If I instead say, oh no, let's use a universe that's not flat, we're going to make it spherical, and that sphericity will be 0.01, so tiny. Then that comes to the blue, that would move the predictions down to this blue line, not in as good agreement with the data. That's only for 1% in curvature. Alternatively, we said, oh no, let's leave the universe flat, but we'll let the cosmological constant vary in time. Here's a W of -0.7 model. That would cause things to change like this. Again, not in very good agreement with the data. So you can see that this data, we have percent level agreement here with the predictions of the flat cosmological constant model, perhaps the simplest model. But deviating from that actually gives us a very sensitive test of that. So this is, now if you allow both of these to vary, here's the curvature and this W parameter, and here's the constraints from the microwave background plus all these BAO measurements, and that star is where this simplest model is. And you can see we're really now pushing down to sub-percent precisions in the curvature, 10% precisions in this parameter W. It's really very strong argument for this particularly simple cosmological model. A famous cosmologist, Alan Sandage, described observational cosmology as a search for two numbers, H0 and omega matter. So this was in the older days before we were talking about dark energy, but basically H0 is allowing you to measure the age of the universe or the typical size of the universe. Omega matter is this question about the ratio of the matter to the critical density. And the combination of modern data really gives superb constraints on this. We're now talking about Hubble constants of 67 plus or minus 2 kilometers per second per megaparsec. So in other words, we've measured the age and scale of the universe to about 2%. Omega matter, again, about latest data is about 0.3 plus or minus 0.016. Really very, very precise measurements of the density of the universe. So I'm now going to turn it back over to John for the last segment here.
So what I'm going to do to finish is to try and connect some of the measurements you've heard about to a few broader issues in cosmology, which are going to, in part, motivate where we're trying to take this sort of research in the future. When you stare at this, you think somebody's having a joke on you, that the universe is made up out of all these distinct components, all of which, to astronomical level of precision, have the same value. Why do we have to do the same thing 3 times over? There must be some connection between them to explain this. And yet, the more you think about these different constituents, the more surprising it is that they're at this level. So there are various approaches to this puzzling model. I mean, for a long time, quite a few people tried approach number 1. And as I tried to indicate, I think if we'd only had the data from supernovae, the majority of the astronomical community would not have been prepared to accept the universe was dominated by dark energy. They're complicated astronomical objects. There are plenty of ways you could think about it in principle how that could all have gone wrong. But it's only the agreement between different lines of argument that mean that number one is not viable any longer. Number two, the cosmological constant, has the longest lineage. It was there right from the first relativistic theory of gravity from Einstein in 1915. He added it in 1917. Ironically, just at the time the first good data for the expansion of the universe were becoming available, his motivation was actually to understand how the universe could be static. His argument, in fact, is one that could have been made centuries earlier, just in the context of Newton's treatment of gravity. And anybody who's interested really should try and read a translation of Einstein's 1917 paper. It's beautifully simple. If you know gravitation theory, you recognize Poisson's equation that says del squared of the gravitational potential is proportional to the density. But a static universe that would have to have no gravitational force pulling matter together, so the potential has to be a constant. But then that means this side is zero, so the density would have to be zero. So a static, non-zero density universe is impossible in Newtonian gravity. And Einstein said what perhaps Newton should have said, is that therefore this tells you this equation is wrong, and you have to modify it. And you could just add a constant number here, so the potential is now constant, but this constant balances the density on this side, so the equation works. You could move this number over here, and then it's just a contribution to the density of everything. It's a density of empty space. So Einstein invented the idea of a density of empty space. As I'll show in a second, actually, Nernst, the thermodynamic pioneer in 1916, was the first to make the argument that from quantum mechanics, you might expect that this number would be non-zero. Subsequently, we've moved upon models that Daniel hinted about, which is a dynamical dark energy, that is an energy density that is changing its value with the time. And then at the end, I'll say a few words about the role of the observer in interpreting all of this. But briefly, the energy density of the vacuum. What is the vacuum? Its space contains absolutely nothing. Well, that means no matter, no light as well. But light is fluctuating electromagnetic radiation. It's lines of force that have perturbations on them. Could these lines of force be completely flat? Well, no. The uncertainty principle forbids perfect knowledge of position and velocity. There must be some residual energy. It's called the zero-point energy. So even if you take all the photons that exist in the box away, there's still a half times h times the Planck's constant. This is not the Hubble constant, this is Planck's constant. A half Planck's constant times the frequency per mode is still present. And as I said, Nernst, I only learned this recently, was the first to add all this up. But in cosmology, it was publicized by the great Soviet cosmologist Zeldovich in the 1960s. And he realized that you would exceed the total possible energy density of the vacuum. Of course, in the 60s, we only had upper limits rather than, as we do today, a measurement. Unless, if you included photon energies, anything above about 1,000th of an electron volt. Right? Now, we have seen gamma ray photons that have something like 10 to the 15 electron volts in energy. So we know that photons can be a lot more energetic than this. So there's a big problem in the energy density of the vacuum, which is called the scale problem. There's also a problem we call the why now problem. We've seen this plot before. The matter density declines as the universe expands, matter becomes diluted. The vacuum density just stays constant. And they cross over just at one point where we happen to be living. What a coincidence. Can these be related? Well, one way you might understand that the vacuum density has a value that's much lower than what seems to be its natural value was produced by my Scottish compatriot, except Peter Higgs, like me, also was not born in Scotland, although he spent most of his life living there. He was trying to solve a completely different problem, that is the origin of mass in particle physics. But in order to do so, he had to invent a thing called the Higgs field, except being a very shy man, he hates to use the word Higgs boson or Higgs field. It's very funny to try and force him into a corner where he has to say it. He invented, though, a thing called a scalar field. What is it? Well, nobody knows, actually. Physicists talk a lot about fields like the electromagnetic field. We have no idea what they are. They're just things that fill space somehow, except the electromagnetic field has a direction associated with it. A scalar field is just a single number of something. But what Higgs said was that whatever this something is, it produces an energy density, V, which depends on the number phi. So phi has a value throughout space. The associated energy density has a value. And this is his picture of how that energy density varies according to the field. So you have a picture where as you change the field, the energy density can alter as the field rolls downhill, as it were. So this is very interesting for cosmology because, after all, we know now that the Higgs field exists. And if there are other fields like the Higgs field, it gives us a possibility of a cosmological constant that could change its value, allowing it to roll from a high value down to the low value that we observe. So this is one of the reasons why we very badly want to know if dark energy changes its density with time. There's another way out, though, which I didn't have on my list, which is that everything that you've heard so far is wrong. For the following reason. Why do we believe that dark energy has to be present? It's present because we observe the expansion history of the universe. And you can write it in this form, the Friedmann equation. The Hubble parameter, the thing in Hubble's law between distance and redshift, changes with time, or indeed with redshift of the era. It's its value today times a whole pile of stuff, which depends on what the density of the universe is at that time. And you add in everything you can think of, matter, getting more dense at high redshift, and you can't match the data that we've been showing unless you have a term in here which is more or less constant. So there's a saying in computing, garbage in, garbage out. We've assumed that Einstein's theory of gravity was correct to get this equation. We've deduced that dark energy must exist. But maybe we had the wrong theory all along, in which case dark energy doesn't exist. Well, you might think you can't tell the difference, but we've shown you something today which can discriminate between these, and this is the redshift space distortions, which have now taken on a completely different role in cosmology from the one that we first thought of. A decade ago, we saw redshift space distortions, the peculiar velocities, as a way of getting at the density of the universe. Well, now we know that very accurately. We can take that as a given. And we can measure redshift space distortions much more accurately. And here's the latest data from SDSS 3. Absolutely gorgeous. The picture I showed you before from 2DF only went out to about here. We were looking at the central part of this. Now we've expanded it. Here, actually, you see the baryon acoustic oscillation ring. It's 100 megaparsecs. And everything in between is flattened by the Kaiser infall. So we measure that very precisely. What it's actually telling us is the rate at which density fluctuations are growing. It depends on the density of the universe, yes, but it also depends on the theory of gravity. So if the theory of gravity is wrong and gives us the acceleration of the universe without dark energy, it quite plausibly would change the rate at which structure is growing. But so far it doesn't seem to. Here's a graph of a number which I don't need to explain the units of or the notation, but it's proportional to the rate of increase of density fluctuations. High numbers mean that density is growing at a high rate today against redshift. And it's now been measured from our first measurement, 2DF GRS, at the lowest redshifts, right out to a project I'm also involved in called Vipers, almost at redshift 1. And in between, I'm sorry, this wasn't done deliberately, this is not by me, the most accurate measurement, the boss one that Daniel was responsible for, sits here. Again, here is the standard line, taking the cosmological parameters of density and so on as measured from CMB data from Planck, etc., plus the assumption that Einstein was right about gravity. And you'll see at the kind of 10% level, it matches the data. There are other ways of getting a handle of this. I mentioned already gravitational lensing, the fact that light from galaxies behind foreground massive galaxies gets deflected. This is a great way of probing the expansion history of the universe through the distance redshift relation. So the amount of distortion here in this ring depends on distance. The further behind this foreground lens I put the background galaxy, the greater the distortion will be. So this is another way of probing the properties of dark energy. And actually, potentially, it's the most precise. The trouble is that although here you see a colossal distortion, it's a special region of sky with a thunking great foreground thing. Mostly, background galaxies are distorted so that a circular galaxy would become elliptical by 1%. And you want to measure that 1% very precisely. So this is pretty challenging, but with huge imaging surveys, it's possible. So lensing and redshift space distortions are the new weapons in the armory. Here's a graph that summarizes where we are. The two axes on here show you the fractional deviations in the strength of gravity from the standard value. So I've already shown you the horizontal axis, which comes from the redshift space distortions, consistent with no change in the strength of gravity to roughly 10%. Gravitational lensing, you can do the same thing. You can ask, does light get deflected by concentrations of matter at the rate expected for standard gravity? And yes, it does. And this is a non-trivial thing, because light in Einstein's basic theory falls twice as fast as ordinary material particles. And it was the detection of that factor 2 in 1919 that really established the correctness of general relativity in the eyes of the world. So we're now probing that factor of 2 and finding that, yes, on cosmological scales, it still applies. Finally, we've already had it emphasized from Daniel that we know that this effective equation of state of the dark energy is something like -1 to within 5 or 10%. So another way of putting that, if you don't like this obscure notation, is that if you consider the energy density of the vacuum at redshift 1, when the universe was half its present size, to the value it has today, those values are the same to within 5 or 10%. Dark energy is not evolving. So far, it looks like we have to think seriously that the universe contains standard gravity and dark energy is a physical substance. So we still have all the problems associated with dark energy, of its size, and the fact it's becoming important now. The only solution that I know of that offers us a hope of solving these problems, I wouldn't say it was at all widely accepted in the cosmological community, is the anthropic one. This is controversial because, if you like, it breaks the kind of Copernican approach to science in which we say that the role of the observer is unimportant. We heard earlier on in response to a question that everybody in a uniform expanding universe thinks that they are at the center. So does the observer matter? Well, it does to an extent. The temperature of the microwave background today is 2.7 Kelvin. It obviously can't be 100,000 Kelvin, otherwise we'd be fried. We have to live late on in the universe. But what's much more radical in the anthropic approach is the suggestion that there may be a multiverse. That is, that we could have, in some genuine sense, a set of universes like our own, each one having a different value of the cosmological constant. If so, we need some new physics that allows different values of the cosmological constant to be present. And this kind of Higgs-like scalar field is one possibility. Anyway, the question is, what would the consequence of that be for structure formation? And the answer is radical, because we've seen that gravity makes structure grow. It assembles galaxies and superclusters by matter pulling itself together. But if the universe is dominated by the density of the vacuum, that process switches off. So as soon as the large-scale structure that we've seen in the galaxies today is more or less as it will be forever now, because the universe is becoming vacuum-dominated today. So therefore, if the vacuum had had a much higher density, none of that structure, including us, would ever have come into being. Moreover, this, in some sense, this multiverse is a prediction of modern cosmology. We haven't spent much time in this presentation. We've gone on long enough, I know you're all thinking, but we haven't talked at all about the most interesting, exciting part, which is the initial conditions, how the universe got going. This is the theory of inflation, which, believe it or not, is assumed to be driven by yet another scalar field, not the Higgs field, not the scalar field that drives the current acceleration and causes dark energy, but a third one. That scalar field suffers quantum mechanical fluctuations because the universe is, at that time, extremely small. And it's those fluctuations that are supposed to seed what we see in the microwave background and so on. Well, in this picture, the inflation field is rolling downhill, trying to reach the bottom and end inflation. But the fluctuations are getting in the way, and the fluctuations can actually kick it back uphill. So in simple models of inflation, actually half of space, inflation never ends. It continues forever, every now and then blundering close enough to the bottom of this potential that inflation can finish. And each instance of that causes a new bubble universe. So inflation actually predicts that this multiverse exists. It's a necessary part of the theory of initial conditions, if we think that's correct. So there's some substance to thinking this is a sensible approach. And actually, a long time ago, a very eminent physicist, Steven Weinberg, winner of the Nobel Prize in physics for the invention of the standard model of particle physics, but also a great cosmologist, thought about this problem that I've outlined, that the cosmological constant should be much, much larger. And he thought about observer selection, saying that observers wouldn't be around to see large values. And he even made a prediction that if the anthropic principle accounts for the smallness of the cosmological constant, we would expect a non-zero value. He was predicting the observations that we subsequently made. So that ought to be impressive, that in science, we try to make predictions, we try to rule them out. This one could have been ruled out, and it wasn't. Well, how do we sort all this out? The impression I've tried to give you is that we're looking to understand, first of all, whether the theory of gravity is right. Secondly, whether dark energy is evolving at all, whether we have any hint of the dynamics that could help solve this size problem. So we need larger surveys. I'm afraid it's just rather unimaginative. It's more of the same. It's been a great success story. We haven't reached the limit of what we can do. The next thing on the block will be what you might call a super 2DF. So this is the Kitt Peak 4-meter telescope. It's the same size pretty well as the Anglo-Australian telescope. And it'll have a similar field of view, a bit bigger, 3 degrees instead of 2 degrees. Instead of 400 fibers, it will have 5,000. And that should get going in roughly 2017, if all goes well. We're still fundraising, so we'll pass around a hat at the end, okay? It will do the same sort of broad spectrum mix that Daniel Eisenstein outlined for SDSS. It'll look at ordinary galaxies. It'll also look at quasars, covering the redshift range right out to redshift 3 or beyond. Except now, we're going to end up with about 20 million galaxies, several million quasars. So we expect that this precision on the Hubble parameter as a function of redshift should have these sort of error bars, which at their best will be sub% precision. So we're going to measure the evolution of the equation of state of dark energy very precisely. After that, well, of course, all these projects slip. It's rather funny. I remember the very first meeting of the 2DF consortium we had, which was in about 1995. We knew that Sloan existed as a project, and they were much larger than us, and there was a danger that we would be crushed. So I remember saying, we've got to get our results out quickly. We mustn't slip. We've got to be done by 1998. And of course, we published our first papers in 2001 and finished up in 2005. We'd slipped hugely. So did Sloan, fortunately. These projects will all slip, and many people have sleepless nights around the planet wondering just by how much. This is the one where the stakes are highest. It's done in space. Space is very expensive. So this is a European Space Agency satellite called Euclid. And it's actually grew out of initial motivations, partly to exploit this gravitational lens signature. And indeed, there was an experiment I was involved in called the planning off, called June, the Dark Universe Explorer, which had a beautiful logo. This was to do gravitational lensing only, but it got merged by the European Space Agency with a competing project called Space, whose logo wasn't nearly as pretty, which was motivated for doing baryon acoustic oscillations. So in, let's see, 2008, ESA decided these were going to be merged into a single explorer of fundamental cosmology using gravitational lensing and BAO. And this created the Euclid satellite, which we hope will be launched in about 2020. It's going to cost 600 million euros. And it's terrifying to think that we spend these sums of money on science targets that evolve. Because notice, I said BAO, not RSD, because it was only around about in 2008 that people first realized that the redshift space distortion effect was one of the premier probes of the theory of gravity. So it's quite alarming planning these projects over these decade-plus timescales to hope you hit the right target at the end. Euclid's spectroscopic technique will be completely different to the one you've heard. No fibers, no moving parts. You don't want moving parts in space. Instead, it's what's called slitless spectroscopy. That is, you simply take an image of the sky and you place in front of that a dispersing element that puts the wavelength from different frequencies in different places, not just for the objects, but for every pixel on the sky. And so all of these things now get stretched out linearly into these spectra. And you might look at them and think, well, those spectra overlap, don't they? Don't they interfere with each other? Yes, it's going to be a complete nightmare. But potentially, this is very powerful. Predominantly, of course, most of the spectra won't overlap because all we'll see are little dots like this. So the H-alpha emission line, characteristic of hydrogen being excited by star formation. If you don't see anything but that, you might wonder how you know it's H-alpha. That's also a good question. This will be very challenging, but if it can all be made to work, we'll get something like 30 million redshift and extending up to the very high redshifts that DESI can't reach. So in 2025 or so, what are we going to have? We're going to know well enough over the whole baseline between the present and redshift 2 or above, sensitive measurements of the distance scale of the universe and the rate at which structure is assembling itself, so that we will be sure that if the dark energy density is varied by even 1%, that we can detect that. And similarly, if gravity has changed its strength by 1% away from the standard value, we'll see that. We don't know whether either of these deviations will be seen. Fortunately, there's a great deal more of physical interest, for example, the mass of the neutrino, that's guaranteed to come out of these surveys. So we'll win whatever happens. So let's finish by going right back to the beginning and completing this curve. Again, just let's think. This whole story only started just over 100 years ago. The very first redshift was measured by Schleifer in 1912, published in 1913, which was the year my father was born. So this has all happened, in a sense, in a human lifetime. We've built up to the present state of knowing many millions of redshifts. DESI and Euclid will take that up to 100 million or so, perhaps, total. And look up here. I've got a line labeled HUDF, the Hubble Ultra Deep Field. That's the deepest image of the sky ever taken, and it counts basically every galaxy there is. You're looking through the entire universe. So there's a kind of Moore's law going on here, which clearly, at this rate, by about 2050, means we're going to run out of universe. I would never have dreamt, if somebody had made that suggestion to me, even 10 years ago, never mind 20, I would have thought they were fantasizing. But it's clear where this subject is going. It's extraordinary how far we've traveled. So I think that's the end of our presentation. We've learned a colossal amount about the universe we live in. It's a very special and exciting time, the privilege to have made small contributions to this story. But there's a huge amount that we don't know. We haven't started to figure out what the dark matter is. As you've heard, we've no idea what the dark energy is, and whether we will ever know is unclear. The theory of gravity is in good shape so far, but it may fail as the data improve. we see these beautiful fluctuations in the distribution of matter and light around us. We'd love to know, we'd love to verify the theory of inflation, which has been around now for 30 years, still not proved, although many people tend to forget this, as to whether this originated from quantum fluctuations. And last of all, the idea that, in fact, to answer some of these questions, we may need to go beyond the idea that we live in a single universe to realizing that we are part of a colossal connected network of multiverses. Well, sorry, not connected. One of an ensemble of multiverses whose existence we can dimly infer from solving some of these problems, but that we can never explore. In some sense, it's the end of science. But I think you'll agree that science has done pretty well so far. So on behalf of all three of us, I'd like to say thank you to the Shaw Foundation for the truly humbling honor that's been done to us in awarding this prize. And it's been a pleasure to have the opportunity to come here today to tell you about some of that work. Thank you very much.
We are running late, but we probably have time
You should turn on for
one or
questions.
two questions if somebody wants to ask. Okay. Yes, Robert.
So, at the levels of
wait for us. Microphone. Sorry.
So at the level of precision that you're talking about, is it possible that the cosmological principle, variations in the cosmological principle, could cause any of the issues you're talking about?
The question was, is there a possibility that variations in the cosmological principle could be dealt with here? So the cosmological principle is, in a sense, violated by the anthropic principle. The cosmological principle says, in effect, that the properties of the universe that we observe from our location should be characteristic of all locations. So from our point of view, on the larger scales, the universe is isotropic, it's the same in all directions, and it's homogeneous. Now, of course, it's possible that beyond the scale that we can observe, those are violated. So look at this carpet, it's nice and smooth and uniform. You might think after a while it would go on forever, but of course, it has an edge. So we can only observe out to 13 billion light years away. And what happens beyond that, it's a leap of faith that it's more of the same, yes.
Okay.
Please bear with my naive question. So if the dark energy is indeed a constant and the universe is also expanding, then is it true that the universe is getting more and more energy?
Well, you have to trade that off. You're revealing more energy in that form, but you have to trade it off against the, an object that's smaller has more gravitational potential energy. So as the universe gets bigger, you're trading off gravitational potential energy for energy in these other forms. So the net energy doesn't need to change, although I think that's the simplest way.
Yeah, but this is a very difficult question in relativity, what the total energy of the universe is, particularly if it's infinite. But the best you can say is that in all of this, energy is conserved. And so you might well ask, here I have a sphere of nothing, it's the vacuum, but I say, the vacuum has a density. So I make this sphere bigger. Well, it has more volume, and if the density is the same, there's more matter inside it, so more energy. So where did this energy come from? And the answer is that the vacuum not only has a density, it has a pressure, or actually a negative pressure, a tension. So to stretch the sphere of vacuum, you have to do work against the tension. So in this sense, energy flows across the boundary. Okay, so that in the same way as if you have a bike and you pump up your bicycle, the air inside the pump becomes hotter, and that's because of the work that your arm is doing against the pressure. So locally, energy is always conserved, but of course, if there's more vacuum globally, there's more energy in the universe, it sounds like. But it's best just to think of energy as being conserved locally. That way you can have a good sleep at night.
Okay, maybe last question.
You talk about the future. So how is LSST going to help?
Okay, the question was, how is LSST going to help? LSST is the Large Synoptic Survey Telescope. Don't need to say what synoptic means, probably because most astronomers aren't quite sure. Yeah, LSST is a ground-based imaging telescope. Okay, so it's like the spectroscope. It's like the first part of SDSS, but instead of being done with a telescope diameter of 2.5 meters, it's being done with an 8-meter telescope. That will also be operating in the mid-2020s on current planning. It will try to do some of the same science. It will, because it's an imaging experiment, it can measure gravitational lensing. From the European point of view, and this is an American experiment, the most important part about it is that it will measure photometry of galaxies in many different wavebands in the same way as SDSS measured ultraviolet through to near infrared light. Euclid needs that because Euclid will only measure the lensing distortions of galaxies in a single waveband. And these galaxies are so faint, it's impossible to measure their redshifts by direct spectroscopy. So we have to resort to a cheap and cheerful method called photometric redshifts, which means basically you take a galaxy spectrum which has some broad shifts in it, and you move it around until it matches the photometric data taken in all the different bands. In this way, you can measure a redshift to a precision of maybe 5% or so, which, you know, for billions of galaxies is not bad. But you can only do it if you have all the wavebands. So LSST will provide that, which Euclid cannot.
Okay, time is late, and let us thank the three speakers for a fantastic lecture.
Well, no,
I should point out that this lecture is packed with information, and I doubt anybody can absorb all the information. But if you want to learn more, they will go to they will go to Science Museum tomorrow at 2:30 for a forum, and you're welcome to go and probably have the time to ask the question you still have in mind. So, okay, thank you.